we did inverse Fourier transform of 2 pi into delta omega minus omega naught. We found that to be equivalent to e power j omega naught t. And also inverse Fourier transform of summation k equal to minus infinity to plus infinity 2 pi ak delta omega minus k omega naught. So this is the inverse Fourier transform, that is equal to ak e power j k omega naught. So k equal to minus infinity to plus infinity. Right? So this is nothing but a periodic signal. Right? So this show, okay, so let's start from today's class. So this is what we did towards end of the last class. So this tells us that this shows us that periodic signals can also have, or Fourier transform can also be, okay, let me write in a different sense. Fourier transform can also be defined for periodic signals. Not only a periodic signals, but periodic signals can also have, we can write will also have Fourier transforms, right? So Fourier transform of periodic signals contains impulses. Impulses in the frequency domain. Right. Because delta of omega is what? Delta of omega is an impulse in the frequency domain. That means, yeah, your x-axis is frequency, and at omega is equal to 0, you have omega, you have this impulse. So this is your delta of omega, right? So thus in Fourier series we can have that Fourier series expansion only for periodic signals, whereas if you consider Fourier transforms, we can have Fourier transform for what? For periodic as well as aperiodic signals. So in that sense, Fourier transform is more generic than Fourier series, right? So this is an important concept. So Fourier transform is more generic than Fourier series. Why do we say that? Because Fourier series is applicable only to periodic signals, whereas Fourier transforms is applicable both to periodic and aperiodic signals, right? So if you and one more final point in this is, if you see this, let's write this as the Fourier transform pair. So if you are given a periodic signal, you find its Fourier series coefficient, and then you can find its Fourier transform like this. So as Fourier transform of sigma over k ak e power j k omega naught t is equal to sigma over k 2 pi ak delta omega minus k omega naught. For finding Fourier transform of any periodic signal, what we should do? First find its Fourier series coefficient. We can first find its Fourier series coefficients. And then compute its Fourier transform as, if you find the Fourier series coefficients, multiply that with 2 pi and then add this term delta of omega minus k omega naught, k equal to minus infinity to plus infinity, right? So we'll do at least 3 examples here, which are of interest. Okay, now let's do some examples. Examples of finding Fourier transform of periodic signals. Okay, let's take the periodic square wave. Okay, so let me exactly show this procedure. If you are given a periodic signal, find its Fourier series coefficients, and from there you just use this formula, use this kind of substitution method. So first example is periodic square wave. So till now you have Fourier series coefficients only for this periodic square wave. We haven't defined a Fourier transform. We haven't computed Fourier transform for this periodic square wave. So periodic square wave is something like this. So minus t1 plus t1. This is t by 2. This is t. So this is t by 2 minus t by 2. This is minus t. And so on. Say this is x of t. And this goes on as t. Right? So now our question is, what is Fourier transform of x of t? Now, what we said, if we are given any periodic signal, first find its Fourier series coefficients, and then from the Fourier series coefficients, once you got that AKs, then simply apply the formula Fourier transform is equal to 2 pi into AK and delta of omega minus k omega naught b, right? First find Fourier series coefficients of AK. Sorry. First find Fourier series quotients of x of t. So previously we got that in one of the previous examples we got this AKs to be sine k omega naught t1 divided by pi k. Yep, yeah. So now Fourier transform of x of t is simply substitute k equal to minus infinity to plus infinity 2 pi into, here you put ak, sine k omega naught t1 divided by pi k delta of omega minus k omega naught. That's it. This pi gets cancelled and you will get something like, yeah. So this is the Fourier transform. So this will be 2 into summation sine k omega naught t1 divided by k delta omega minus k omega. So this is simple. First find the Fourier series quotients and then use those Fourier series quotients. So this is AK for us, right? This is the AK, right? So now next let us compute another. Let's take another simple periodic signal. What is one of the simple periodic signals? It's sine, a sinusoid, right? So let's take another example. Find Fourier transform of x of t is equal to sine omega naught t. Yeah. So this you should be able to first try this out. Right? It won't take you more than 2-3 minutes. So I'll go a bit slow here. So we have a periodic signal which is given by x of t is equal to sine omega naught t. We have to find the Fourier transform of this. So what is the procedure I discussed till now? First find the Fourier series quotients of x of t, right? So first find Fourier series quotients or find Fourier series quotients of x of t. Then what is that? So we have seen that x of t can be written as e power j omega. This we did previously. E power j omega t minus e power minus j omega naught t divided by 2j. Right? So that is nothing but by 2j e power j omega naught t minus 1 by 2j e power minus j omega naught. So this is in the form of a1 e power j omega naught t plus a minus 1 e power minus j omega naught. So that implies Fourier series quotients are a1 equal to 1 by 2j and a minus 1 is equal to minus 1 by 2j and ak is equal to 0 for k not equal to plus or minus 1. Right? So when I try to expand this as a Fourier series quotients, and we said that we can do it by inspection. See, when we did this example in not the last class, in the last class, okay, in the last class we got this. So here the Fourier series coefficients are a1 equal to 1 by 2j, a minus 1 is equal to minus 1 by 2j, and all the remaining Fourier coefficients are 0. Okay. Now we got the Fourier series coefficients of x of t. How to find Fourier transform of x of t? So Fourier transform of x of t, you just use these Fourier coefficients. So it will be a1 e power j k equal to 1 here, omega naught t delta omega minus omega naught plus a minus 1 e power minus j omega naught t delta omega plus omega naught, right? So this I'm simply applying this formula, 2 pi into ak delta omega minus k omega naught, k equal to minus infinity to plus infinity, right? So when I apply this formula, I have only a1 here, I have only a minus 1 here, I have only a1 and I have only a minus 1, and when I put a1, it would be omega minus omega naught. When I put a minus 1, it will be omega naught, it will be omega plus omega naught, right? So that is equal to pi by j e power j omega naught t minus pi by j e power minus j omega naught. Oh, sorry, there should be an impulse function here. Sorry. Yeah. So let's compute this in the next page. So we got the Fourier series coefficients. Now, once we got the Fourier series coefficients, Fourier transform is nothing but k equal to minus infinity to plus infinity, 2 pi ak delta of omega minus k omega naught t, right? So I did a mistake here. There should not be e power j omega naught t and a power minus j omega naught t. So please cross this. So what we did was, till now we computed the Fourier series coefficients, and from that we are going to compute the Fourier transforms. So Fourier transform is this. So this is equivalent to 2 pi into a1 delta omega minus omega naught plus 2 pi into a minus 1 delta omega plus omega naught. Because here k equal to minus 1, this minus will become plus. So this is 2 pi into 1 by 2j delta of omega minus omega naught plus 2 pi into minus 1 by 2j. So this will be pi by j. An impulse of strength pi by j minus pi by j. Another impulse of strength minus pi by j. So if you have to show this, the diagram, it will be omega, it is 0, and let us draw this. At omega equal to omega naught, we have an impulse, and that impulse strength is pi by j. So let's call this as omega naught. And we have an impulse, this impulse strength is pi by j. And at omega equal to minus omega naught, So at omega equal to minus omega naught, we have another impulse with its strength is equal to minus pi by j. So its strength is equal to of course this there should not be this minus pi by j because it's already minus, right? Because this is your x of j omega, because this is x of j omega, Fourier transform of x of t, right? So Fourier transform of a sinusoid has only two impulses, one impulse, positive impulse at omega naught, and negative impulse at minus omega naught, right? As a homework, find Fourier transform of cos omega naught. Okay, so the answer that would be, you should get two impulses, again one at omega equal to omega naught and at another at omega equal to minus omega naught, and in this case both impulses will be positive. This is x of j omega. Both impulses would be positive, and its will be, what is its height? So you find out that, like, at least you should be knowing that both impulses will be going upwards, and one impulse at omega equal to omega naught, another impulse at omega equal to minus omega naught, right? So these heights should be equal to pi. This should be equal to pi, this should be equal to pi. So this is a homework problem for you. Next, we'll do one more example of finding Fourier transform of periodic signals, and then we will move on to the properties of Fourier transforms, right? Yep. So one more example is periodic impulse train. This is another interesting example. Another interesting and very important, say for your GATE exams or even university exams. So let's consider an impulse. There is an impulse here. There is an impulse here. There is an impulse here. So this is a periodic train of impulses, and so on. So similarly, minus t, there should be an impulse at minus t, there should be an impulse at minus 2t, and there should be an impulse at minus 3t, and so on, right? So this is your x of t. Sorry. So our x of t is nothing but delta of t minus capital K t, k equal to minus infinity to plus infinity. So there are its period is t. It's a periodic impulse train with period equal to t. Then what is its Fourier transform? So similarly, you can solve this, like First, find the Fourier series coefficients of x of t. How do you find it? Ak equal to 1 by t over one period x of t e power j k omega naught t dt. So that will be 1 by t. So I'll take the period from minus t by 2 to plus t by 2. So if I take the period from minus t by 2 to plus t by 2, I have only delta of t there. So that will be e power j k omega naught t dt, and this becomes and this simply becomes in the integral here when t equal to 0 only, this becomes 1. So it will be equal to 1 minus t by 2 to plus t by 2. So this becomes 1 only at t equal to 0, and it becomes only 1 by t. Now use the formula x of j omega. The Fourier transform is 2 pi into ak delta of omega minus k omega naught. So that is equivalent to 6 summation 2 pi into ak is 1 by t, right here. So ak is equal to 1 by t for all k delta of omega minus k omega naught. That is simply 2 pi by t omega minus so this will be k omega naught. Yeah. So let's see what is the difference between these two. The original signal is summation k minus infinity to plus infinity delta of t minus kt. This is the original signal, and its Fourier transform is, so this is the original signal is periodic impulses in time domain. Its Fourier transform is periodic impulses in the frequency domain, because delta of omega minus k omega naught is there is an impulse at omega equal to 0, there is an impulse at omega is equal to omega naught, and there is an impulse at omega is equal to omega naught, and so on, right? And the impulse strengths are different here, 2 pi by t, 2 pi by t, and so on. So the plot of x of j omega, which is equal to 2 pi by t summation delta of omega minus k omega naught, is so there is an impulse, there is an impulse, there is an impulse, and so on. So this is omega, this omega naught, this is 2 omega naught, this is 0, and this is at minus omega naught, and this is at minus 2 omega naught, and so on. And the strength of each impulse is what should be the area of each impulse, or what should be the strength of each impulse here? See, we are trying to plot this signal. So it will be 2 pi by t. 2 pi by t. So this is your x of j omega. So thus Fourier transform of periodic impulses, of periodic impulse train in time domain is periodic impulse train in frequency domain, right? So if we take periodic train of impulses in the time domain, then and if we do the Fourier transform, we get another set of impulses in the frequency domain. Remember, x of j omega is the frequency domain representation of the signal. We will be given in general a time domain signal x of t. So whenever I specify a function in the time domain, it is called a time domain signal. So x of t is a time domain signal, and when I find x of j omega, where omega is equal to frequency, it's the frequency in radians, right? It's the angular frequency, radians per second. Omega is the angular frequency in radians per second, and then x of j omega is the same signal in the frequency domain. So x of t is the time domain signal, and x of j omega is the frequency domain signal. So what is this example saying is that if we take a set of impulses that are periodic in time domain, we get and transform it into frequency domain using Fourier transforms, we get a periodic set of impulses in the frequency domain as well. So this is one very important signal, and whose applications you will find later. Okay, so okay, so here one last point is, what is omega naught? Omega naught equal to 2 pi by t, right? Because we know this fundamental. So t is the fundamental period, t is the period, fundamental period, and omega naught is the fundamental frequency, it's the frequency. So another thing is, if t increases, this frequency decreases, right? If the period increases, frequency decreases. What is the simplest example of this? Say even if you take a sine wave, and if you take a sine wave of very small period, it's a high frequency, right? So its period is this, its period is this, and its frequency is something. But if I increase the periodic, if I increase the period now, so if I increase the period, then it's a low frequency. We call this as high frequency, and this is low frequency, right? So similarly here, if t increases, the frequency decreases, or t decreases, frequency increases, right? So there is you already know from your first year courses that inverse relation between frequency and time, between frequency and when I say time, it's a period. I'm talking about the period of the signal in time. Okay. So let's move on to the last topic in Fourier transforms, which is properties of Fourier transforms. Properties of So in other words, whenever we write x of t double arrow x of j omega, it implies the Fourier relations. X of t equal to 1 by 2 pi minus infinity to plus infinity x of j omega e power j omega t d omega, right? And x of j omega is minus infinity to plus infinity x of t e power minus j omega t dt. And it also implies that Fourier transform of x of t is equal to x of j omega, and inverse Fourier transform of x of j omega is equal to x of t. See, this notation we haven't done till now, right? This f inverse denotes inverse Fourier transform. So f inverse denotes inverse Fourier transform. That meaning, instead of writing inv Fourier transform, instead of writing inv ft, I'll write simply as f inverse. F inverse is inverse Fourier transform. Okay, so this is the notation we follow. With this notation, let's start with the properties. Fine. So f of x of t is Fourier transform, f inverse is inverse Fourier transform. So the first property, again linearity. Again, it's very simple to derive. So what does it says? If x of t, the Fourier transform of x of t is x of j omega, and if Fourier transform of another signal y of t is y of j omega, then some a into x of t plus b into y of t, what is their Fourier transform? Let's fill this blank. So can you guess? You know it. You have the linearity property in Fourier series, right? So you must have already learned the linearity property in Fourier series, which we discussed 2 classes back, and you must have studied it anyway because the exams are very near, right? So it will be simply a weighted linear combination of the Fourier transforms of x of t and y of t. Okay, so let's derive this. It's only one step answer. So some of you might have already done this. So here simply I'll take a into x of t plus b into y of t. This I can write this as a into 1 by 2 pi x of j omega e power j omega t d omega, because I know that x of t can be written as the Fourier transform of x of t is x of j omega, and I know that x of t equal to this plus b into 1 by 2 pi integral y of j omega e power j omega t d omega, right? So this I can write this as 1 over 2 pi a x of j omega plus b y of j omega. I'm simply clubbing these two integrals, that's it. E power j omega t d omega. It's minus infinity, it's plus infinity. Yes. So this is nothing but Fourier transform of A into x of t plus B into y of t. That's it. So we can fill this blank as A into x of j omega plus B into y of j omega. Right? So some of you, as I said, some of you might have guessed it when I wrote this blank. So in place of x of t, I have put its Fourier integral. In place of y of t, I did put its Fourier integral. And then I simply joined these two integrals. And then I got the Fourier transform of, because whenever I can write something as 1 by 2 pi integral minus infinity to plus infinity into something multiplied by e power j omega d omega, that will become Fourier transform. Right? Okay. And more importantly, it can be extended to any number of signals. See, this is another interesting thing. Some of you may get confused that is it valid only for two signals, or can it be done for any number of signals? Right? So it can be done for any number of signals. Say if we have signals x1 of t, x2 of t, x3 of t, and so on up to xn of t. So it's simply Fourier transform of summation of n equal to 1 to capital N, maybe some alpha n xn of t is equal to summation n equal to 1 to capital N alpha n xn of j omega. So this is the general equation. General linearity property. Right? Okay. So we are done with linearity. Next one is time shifting. What is time shifting? If x of t, Fourier transform of x of t is x of j omega, what will be the Fourier transform of x of t minus t naught? Let's denote this as blank. Okay, so you can try doing this. I'll give you the first step. So this is nothing but x of j omega, sorry, there is no minus, for j omega till t d omega. So find x of t minus t omega naught is 1 by 2 pi. Yeah, complete this out. I'll just close the curtain. There is sun coming in. There is transform. The Fourier transform will have the same magnitude as the original signal, but only its phase changes. Right? Say for example, there is a question. That x of t is at the Fourier transform of x of t is j omega. find true or false. Okay, yeah, just give me a minute. I'm trying to frame a question here. So let y of t equal to x of t plus 7. Then and let the Fourier transform of y of t is y of j omega. Then y of j omega, magnitude of y of j omega is equal to magnitude of so find about this. You just look at the above property, time shifting property, and in fact I told you the answer already when I said when the signal is moved to the left or to the right in the time domain, the magnitude of the Fourier transform will not change, but only the phase of the Fourier transform will change. See, let me remind you once again that a Fourier transform can be a complex value, right? X of j omega can be real value or it can be a complex value. That's why we talk about its magnitude and phase, right? So when a signal is moved only in the time axis, either to the left or to the right, then the magnitude of the Fourier transforms will not change. Only its phase will change. So in this case, this is true. And if you are asked to give the reasoning, you have to give the reasoning using this property, time shifting property, right? And then let's move on to the third property. Okay. Say okay. So before going to the third property, let's take up example of using linearity and time shift. Properties. Say for why these properties are so useful. See, I can give you just one example. We are not going to solve this example fully, but say this is 1, this is 2, this is 3, this is 4, and this is the time axis. And let's say you are given a signal which is something like this. So this is level 1, this is level 2. Say if you are asked to find the Fourier transform of this, you can find the Fourier transform of this directly by using this signal, or you can decompose this signal into two signals where one signal is from here to here. See, finding the Fourier transform of this signal is very easy. We already found it, right? This is nothing but a square wave. So its Fourier transform will be a sinc signal. And let's call this as x1 of t. and you can find the Fourier transform of this signal. This is from 2 to 3. This is t, and this is x2 of t. So this is level 2, and this is amplitude is 1. Here the amplitude is 2. So you can find the Fourier transform of x1 of t. You can find the Fourier transform of x2 of t. In fact, x1 of t you don't find like this. You move it to left and then find, and then you can move it to right again. So this example is solved in 4th chapter of Oppenheim and Wilsky. Right. So this is a very simple example. This is not very like this is not something like highly important or anything like that. But I just wanted to show you the importance of linearity and time shifting. If you have a complex signal, you can divide that into number of subsignals and then apply linearity property. And then say, for example, you can find this Fourier transform in terms of these two signals, right? Okay. So next go to the next property, which is conjugation and conjugate symmetry. Conjugation and conjugate symmetry. So if Fourier transform of x of t is x of j omega, so what will be the Fourier transform of x conjugate of t? See, x of t can be a complex signal, right? So if I know the Fourier transform of x of t, how can I obtain the Fourier transform of x conjugate of t? Is there a relation between these two, or shall I have to do it again? Right. So that's what we want to find out. So let's find out this. So what I'm trying to do, I'm trying to write x of t in terms of its Fourier transform. So x of t, we know that is minus infinity to plus infinity. X of j omega e power j omega t d omega. Now I want to find the Fourier, take the conjugate of this on both sides. So when I take the conjugate, x of j omega will become conjugate of x of j omega, and e power j omega t becomes e power minus j omega t, and it will be d omega. Right? So, but what I want to find is the Fourier transform of x conjugate of t. So to find the Fourier transform, here I need to have e power j omega t, not minus j omega naught t. So replace minus omega with positive omega. So if I do this, what happens is 1 by 2 pi. So this integral, instead of minus omega minus infinity to plus infinity, it becomes infinity to minus infinity. So but both are same, right? So when you take integral from minus infinity to plus infinity or infinity to minus infinity, it depends on integrand. So it will be x conjugate of j omega e power j omega t minus d omega. Here it would be minus, here it would be plus, here it would be minus. So this becomes, this minus will go away. For that minus to be go away, we should have minus infinity to plus infinity, x conjugate of minus j omega e power j omega t d omega, right? See, whenever I replace omega with minus omega or plus omega with minus omega, I'll have to change this. I'll have to put minus d omega here, minus omega here, minus omega here, and I have to change these integrals. I have to flip these integrals, and then again to get rid of this minus, I will again flip these integrals. So this implies Fourier transform of x conjugate of t is equal to x conjugate of minus j omega, right? So what I should write here? Right? Fine. So this is the conjugation property. Now let's see, when x of t is real valued signal, when x of t is real valued signal, we have x of t equal to x conjugate of t. We have x of t is equal to x conjugate of t. Right? So that implies, what is the Fourier transform of x of t? It's x of j omega, and its Fourier transform is x conjugate of minus j omega. Thus, when x of t is real, x of j omega holds the complex conjugate, what do we call, conjugate and conjugate symmetry. X of j omega is conjugate symmetric. So when a complex number has got this property, that the complex number is equivalent to its conjugate, and when a function, so this is called conjugate symmetry. When any complex valued function has got this property, we call this as a conjugate symmetric property. Next, another important implication of this is, okay, so as as a question, you can do this. When x of t is real, show that real part of its Fourier transform is even is an even function of omega and imaginary part of its Fourier transform is odd, or to be precise, it should be an odd function of omega. So how can we show this? Like, so what I'm trying to ask is, say there is a signal x of t, and let's assume that x of t is a real valued signal, right? So it will have a Fourier transform x of j omega. So what I'm trying to ask you, so what we are trying to show is, let us see whether real of x of j omega is even or not. So we know that when x of t is real, x of j omega is x conjugate of minus j omega. So this x of j omega, I can write this as real of x of j omega plus j imaginary of x of j omega, and that should be equivalent to real of x of j omega minus j imaginary of x of j omega, right? So I'm simply expanding this as this and expanding this right hand side as this, right? So what do we get? So that implies real of x of j omega is equal to real of, sorry, there should be minus omega here, real of x of minus j omega, because this real part should be equivalent to this real part. So real of x of j omega is equal to real of x of minus j omega, and imaginary of x of j omega is equal to minus of imaginary of x of minus j omega. Hence, the real part of x of j omega is even function, and imaginary part of x of j omega is odd function. Yep. Okay. So we have got this conjugate symmetric property, and then we just expanded this as we just expanded this in rectangular form. This is equal to real of j omega plus imaginary of x of j omega, and then we expanded the right hand side also in rectangular form, and then we got this. So when x of t is real of its Fourier transform is even, is odd, right? So next let's go to another property. differentiation and integration. So if x of t Fourier transform is x of j omega, then we can write x of t as 1 by 2 pi minus infinity to plus infinity x of j omega e power j omega t d omega. See, all these properties we are deriving from the fundamental definition of Fourier transform. That's what is more important, right? So, and then let's differentiate on both sides with respect to t. Differentiate on both sides with respect to t. So what happens? dxt divided by dxt by dt is 1 by 2 pi minus infinity to plus infinity x of j omega e power j omega t into j omega d omega, because the differentiation of e power j omega t is e power j omega t into j omega, right? So what does this mean? This means that, right, so now the Fourier transform of differential of x of t can be given as j omega into x of j omega, right? So from this what we can conclude is that dx of t by dt, its Fourier transform is given by right. So when we differentiate in the time domain, in the frequency domain, the effect is equivalent to multiplying it by j omega, right? And by some clever guesswork, of course we can prove it, but we are not going to do that. So we can also show that so this is if we differentiate the signal in the time domain. What happens if we integrate the signal in the time domain? Say there is signal x of, if we integrate that, so this x of tau into d tau, then its Fourier transform will be, see, when we do differentiation it will get multiplied by j omega, but when we do integration it will get divided by 1 by j omega. It will get divided by j omega, so it will be x of j omega plus there possibly there is a additional term x of 0 delta of omega. So what is this? This is, see, when we integrate, okay, so when we integrate a signal, we will also find its DC component, right? So when I integral a signal, I'll find its average value or DC value. So this term caters to that DC term that might result from the integration. Right? So this is called integration property. Of course, I know that we haven't proved, but we just stated based on the property of differentiation. We can prove this. Like I'm not going to prove this right now. You can find this proved in some of the textbooks also. Like whenever they state any of these property, they will also prove it, right? So okay, the most important thing is how can you use these properties? Like the more important thing is not only knowing the properties, but how can we use them? As we have seen that we can use the property of linearity and time shifting in decomposing a signal into multiple signals and then finding their Fourier transforms and then combining them. So similarly here, we'll just do one or two examples of using this integral or differentiation property, and then we'll go to what else is remaining. We have time scaling and then duality. Okay, we have two more very important properties, time scaling and okay. First we'll do examples. Of using differentiation and integration properties. Say for example, you can be asked a question which is something like this: find the Fourier transform of unit step function u of t using the Fourier transform of delta of t. So how do you solve this out? So first of all, you have to recall what is a unit step function, and you have to recall what is delta of t and what is the relation between these two, right? So let's recall what is unit step function. Unit step function is 1 for t greater than or equal to 0 and is 0 elsewhere. So what is the relation between unit step and the unit impulse? So this is unit impulse, right? Delta of t is unit impulse function. So u of t is nothing but integral minus infinity to t delta of t dt. So first recall what is unit step function, then find out then recall the relation between u of t, the unit step function, and the unit impulse function. So this we covered in one of the first chapters, the relation, the study of basic signals and their relations. And then what do we call? So let the Fourier transform of we know that Fourier transform of delta of t is equal to 1. Okay. Let Fourier transform of, see, we should have some notation, right? So u of t is the time domain signal, and let's call its Fourier transform as u of j omega. Okay. So when this is the case, from, and this also I call it as d of j omega. See, we know that Fourier transform of delta of t equal to 1, but just for notation sake, just for having some notation, and for us to write some equation, we will indicate that Fourier transform of delta of t as d of j omega, and that, so I can write this as Fourier transform of delta of t d of j omega equal to 1. From the integration property, you have u of j omega is equal to 1 by j omega into d of j omega plus pi into d of 0 delta of omega. So that is equal to 1 by j omega into 1 plus pi into 1 because d of j omega is equal to 1 and d of j omega at omega is equal to 0 is also equal to 1. So I have substituted 1 here, I have substituted 1 here. That's it. Right? So Fourier transform of u of t is equal to 1 by j omega plus pi delta omega. See, this you can also do it directly by using this definition. You can also find the Fourier transform of u of t directly using the definition of u of t. But if you are asked to find the Fourier transform of u of t by using the Fourier transform of unit impulse, then you have to use the relation between the unit impulse and the unit step function, and then use the integration property to find the Fourier transform. And another, and as a homework, you can also do this. As a homework, find the Fourier transform of delta of t, finding the Fourier using the Fourier transform of u of t, and the differentiation property. It's just I'm asking you to do the reverse. There we used the Fourier transform of delta of t to find Fourier transform of u of t, and in that process we used the integration property. Here I am asking you to find the Fourier transform of delta of t using the Fourier transform of u of t, and in this process you have to use the differentiation property. Right? And there is one more interesting example. Example 4.12, the 12th example. Do the example 4.12 in the text. In the textbook, open him. And we'll see. So this is a simple but interesting example. There you are asked to find the Fourier transform of this signal. So this -1, this +1, and this 1 and this -1. So this x of t. See, when you are given any such complicated signals, so don't get panic or don't get too much worried, but try to think what properties you can use in finding the finding the Fourier transform of such signals. Can you split that time domain signal into multiple other signals in time domain and then find their Fourier transforms and then club them using linearity, time shifting properties? Or can you use differentiation properties and integration properties, right? So you look at this example. This is a fully solved example in that book, so it is solved completely, so you will not find any problem in understanding this example. So this he will decompose into two signals and then use the differentiation and the integration property. Okay, then we'll go to the time scaling property, and then with that we'll stop. So next property is time and frequency scale. Okay, so here again we know that x of t Fourier transform is given by x of j omega. Then we want to find the Fourier transform of x of at. So how do we find the Fourier transform of x of at? So let's write x of t. Again we are writing that 1 by 2 pi minus infinity to plus infinity x of j omega e power j omega t d omega.